We propose a method to deform highly detailed models in real time and to interactively create complex and long animations on a standard PC. Using a core set of nodes, our method allows to obtain plausible deformations and animation sequences for highly complex models in real time. Our deformation module starts by sampling the volume within the object with a core set of deformation nodes. A very small number of nodes is sufficient to reconstruct global, visually pleasing shape deformations. The coupling of the nodes is done in a way that respects the topology of the original object. Each node has a finite support radius, within which its influence on the vertices of the shape decays smoothly. The deformation of each vertex on the shape is then defined as a linear combination of the deformations of nearby nodes. We use meshless finite elements to define interpolations which are guaranteed to have first-order consistency, resulting in a plausible deformation field which preserves shape features. The complexity of our problem depends only on the number of deformation nodes, and interpolating the deformation field to the shape vertices is very simple and is done on the GPU. As a result, even for a model consisting of 500,000 vertices, we achieve interactive frame rates. We extend our efficient deformation module to an interactive method for creating long, complex animations on a standard PC. We add time dependency to our energy function, which penalizes acceleration to create smooth, interpolating deformation between frames. The number of variables during optimization is kept low, by only defining deformations at certain keyframes and using meshless modeling to interpolate the motions in between. We propose an adaptive sampling technique, which only introduces frames at problematic regions where the energy is high. As you can see in the bottom inset, pure linear interpolation from two frames results in undesirable collision and distortions. After introducing a frame in the middle, the error is greatly reduced, but the animation still suffers from noticeable distortions. Successively introducing more intermediate frames results in a final time-dependent deformation field that is locally rigid, volume-preserving, and smooth. To disambiguate between possibly many local minima of the energy function, our method allows the user to interactively modify the intermediate deformations without creating handle constraints. Here, by specifying the intermediate position to be above the obstacle, the user creates an animation in which the armadillo goes over the box. We incorporate time-dependent collision penalties into the energy function, which allow us to create animations with moving obstacles. Using our sparse representation of the deformation field together with adaptive temporal sampling, long and complex animation sequences can be created efficiently. After the user specifies keyframe positions, our method creates visually plausible animations. This would be very difficult or even impossible by forward physics-based simulation. Because the number of variables is kept low, the resulting nonlinear problem can still be solved efficiently on a standard PC. This makes our method simple, intuitive, interactive, and fun to use by the animators.